Good morning. Good morning, class. Good morning. Nobody brought me an apple yet. I'm really sad.
You said that you did a PhD and an apple a day keeps the doctor away. And we like
Giving me an apple will make me go away, maybe. Maybe. So what do we got? Like a week left? Like 9 days left. Did anybody notice that on the syllabus there's no class this Thursday? It's there. It's written in black and white. I have no idea why. I asked somebody, I said, is there like no school on Thursday this week? I said, no, there's school. But we didn't schedule anything for this Thursday. I think it was because in my mindless thinking, in my thinking at the beginning of the term, you'd all be busy with stuff at the end of the term. Is everybody busy with stuff at the end of the term? Who's got like lots of exams and stuff due at the end of the term? Who needs extra pressure on Thursday? Just want to test the strain, right? Because pressure gives us strain, right? Yeah, so I'm pretty sure I left it blank on purpose. One, so we could fill in something in case we missed something during the term. And two, so that you wouldn't have so much to do, so you could catch up on other stuff at the end of the term. And it would be an ideal opportunity for you to work on your group project, right? Because on Tuesday, right? Tuesday, we're going to present group projects. And on Wednesday, that's tomorrow, we're going to do the Design of Safety Systems lecture. So we changed that so that you guys don't have to do your group project presentations tomorrow. What are you going to do in your group projects? What's the presentation? I know when it is. What is it? Right? Cost to make the first part, cost to make the second part or the parts after that. Your pricing, and it should be reasonable. I should believe it's going to work. How long will it take to make back the initial investment? That's that initial investment is the cost to make the first part, right? All right, so that's what we're going to do on Tuesday next week. Wednesday next week? Yeah, go ahead.
Do you have any recommendations for where to look to find presses for machines or tools?
What kind of machine?
Let's say
A lathe. I would go to the Haas website, and they have a like build a quote or something like that. It's like when you go to a like a Toyota dealer or something like that. You can go to the website and you can say, I want these options, and it'll tell you how much it costs. Haas Automation. It's the people that make all the machine tools we use in lab. HAAS. But don't like email them and say, I need a quote for these machines, because then they're going to think you're actually a customer and they're going to get all excited because they're going to think they're going to sell you a machine tool and you're not. Yes. Because I know that they have pricing online. To answer that question, their pricing is fully available online. So you can get discounts, but not a lot. The price is the price. So that's why I choose them. And they're so generous to the lab. All right, good. So in order to make good parts, so what is it again we want to do in manufacturing? We want to make stuff with the intent of selling it, right? And often we as the manufacturer get a design from somebody else. So they send us their design, we make it, we send it back to them, and then maybe they assemble it into something and then they give it to their customers. Right. And so we've talked about this, and quality is about giving the customers what they need when they need it. And so what we're going to talk about today is the story the customers tell us about what they need. And a lot of you will be in the position of being the customer someday, right? You won't all be in the position of receiving the information from the customer and making the part. Some of you will be the customer that's designing the parts that goes out for manufacturing, goes out to machining. I think I told you, I may have touched on this story before, but what is it that we send to the manufacturer when we're the customer and we're going to send them something to make? We want them to make us. What do we send them? Well, we try to represent exactly what we want, but what do we physically give them? We give them drawings. What else might we give them? Yeah. Well, we probably don't give them any money until later, but sometimes we do give them money in advance. That's actually part of my story. We might tell them when, so time. We give them drawings. Sometimes we give them the solid model. You guys found when you were using a spree that you could bring in a solid model and then you could extract the features from the solid model to do the programming. So if all you had was a drawing and you didn't have the solid model, you'd probably have to redraw all that stuff when you got to the CAM software. So we often like to get the solid models, but the solid model almost never contains enough information to make the part. It shows us what the shape of the part is. Yeah. So the solid model, although in modern modeling software, I have been told, I haven't experienced it, but that's just because I don't use that software frequently enough to know how to use it well enough to have experienced it. I've been told that you can put tolerancing information directly in the solid model, but typically it's represented in the drawings. And so what are the tolerances again? Yeah.
The most wrong you can be while still being right enough to be useful.
Right. It's the designer telling us, the manufacturer, how much we can screw up and still have made a useful part. And so it's in it, and we talked about this in the measurement lectures where you actually have to have tolerances because we also have measurement uncertainty. So it's impossible to measure anything perfectly. It's impossible to make anything, well, it may be possible to make something that's perfect, exactly the right size. You'll never know if you have. So we have to have tolerances. The tolerances tend to be represented on the drawings of the part. I understand it may be possible to embed it directly in the solid model. I, as a manufacturer that receives solid models, wouldn't know how to get it out of the solid model if you gave it to me that way. I'm going to ask you for drawings with tolerances on them. And so GD&T is today's topic. Geometric dimensioning and tolerancing. Geometric dimensioning and tolerancing is what we're going to talk about today. If I always want to get good parts from my manufacturer, I have to always give my manufacturer good information, correct? What if I want to get good parts from two different manufacturers? Same part, but I want to source some of them over here and I want to source some of them over here. That way, maybe if there's supply chain issues, maybe their shop catches on fire and they don't get to make me the parts. At least I still got some of them because I got them from over here, right? So what if I'm going to send my drawings to multiple different shops? I want all the same parts coming back. So one way we can get good parts from our manufacturer is we send them a drawing, or maybe we just send them a solid model and say, just send me a sample part back. So they could send you a sample part back and you could say, oh, well, this diameter is a little bit too big. Maybe you want to make that chamfer a little bit smaller. And you can iterate with them, right? But you don't want to iterate with two different designers. And what if they suddenly say, hey, we got a much bigger customer and we're not going to make your parts anymore? Could happen. Sometimes the customer gets fired. So then you got to immediately be able to source that out to somebody else. So it's important that the manufacturers over here and the manufacturers over here and the designers all speak the same language. And so GD&T is just a language. And its spelling is more precise than mine, typically. How do you define a language? Yeah. So we have standards. So we typically define a language. We'll have like a dictionary that has vocabulary in it. And we may have rules that define the grammar that we use. So it's the same thing with GD&T. We have standards and we have vocabulary. Now I'm going to exit solo. Go to that one. I'm going to take you guys off the screen and go to the slideshow. So typically we'll have a language to do this, and then I'll press the right mouse. Yes, we talked about that. All right. So there's standards around the world. Many countries have their own standards organization, and they can make their own standards. The United States, we have our own standards organization. We publish our own standards. The standards about GD&T are published by ASME. Anybody know what ASME is? Yes. It used to be the American Society of Mechanical Engineering. Now it's just ASME. They shortened their name so they could be international. But yeah, it's the American Society of Mechanical Engineering, ASME, ANSI, and they have this Y14 geometric dimensioning and tolerancing document. The document, there's a committee of people that actually I know some of the people on that particular committee. There's a committee of people that meet a couple times a year, usually in like a hotel. Like my favorite place to go to these committee meetings is the Hilton at the Chicago O'Hare Airport. And the reason it's my favorite place to go to these kind of meetings is you can go to the meeting without ever leaving the airport. I mean, you do have to go outside security, but you never have to actually leave the airport. There's no need for an Uber. You just walk to the hotel. There's meeting rooms in the hotel. It's actually a nice bar and restaurant downstairs in the hotel. It's a nice place to go for these kind of meetings. So engineers tend to have meetings at places like that. I was on a different ASME committee where I was visiting one of the larger committees, and they were doing their meeting in Puerto Rico at a resort hotel for a week. We fly into Chicago for a day. They go to Puerto Rico for a week. So there are some committees that are cooler to be on. But at any rate, I guess they're doing, the reason they go to Puerto Rico for a week is because ASME, what they do is they publish a book. The book contains the standards. So that other group, they sell more books than we do. That's why they get to go to Puerto Rico and we get to go to Chicago. Anyway, these standards organizations, the publisher of the standard, their job is to sell books. The people on the committee, it's typically volunteers on the committees, their job is to develop this standard language where we can all talk to each other. So in the US, it's ASME or ANSI. And who's had a drawing class? Who had ES 1310 here? About half of you, 3/4 of you had ES 1310. And so when you start a drawing, you have to pick a drawing block to use. They call it a drawing block or whatever, something, the template thing. And so you either pick the ANSI or the ISO template, right? And when you pick the ANSI template, all of the things in your drawing have to conform with the ASME ANSI standard. When you pick the ISO template, everything in your drawing has to conform with the ISO standard. I know this because each organization has written into their standard, if you use anything from our standard, everything in your drawing must be compliant with our standard. I don't know how you enforce that. But It's in there. So it's standards organizations, it's volunteers meet, they get together. What is the purpose of these standards? What is the purpose of the language? It's to promote commerce. It's to enable you guys as the designers to buy parts from them and to buy parts from them. And when you get the parts back, either they meet the specification or they don't meet the specification. And you have a common language to decide whether or not they do. So that's the purpose of GD&T. I could go into explaining how you draw different symbols on the drawing. And you did some of that in ES 1310, right? Did they talk about what symbols to put on the drawing, what the different symbols mean? When I took the class, it was, again, we didn't have all the computers and stuff. We had to twirl the pencil to get the right line thickness. We had to pick the right pencil to get the right line thickness and darkness. But they talked about how to label the drawings. The hard part, though, is, and here's an example, right, of a drawing. So this is a typical drawing. It's got some dimensions on it. It's got some tolerances on it. Here's the part. Yeah, we talked about tolerances before. All right, so this is a sketch, not a drawing. What do I want to do? Yeah, intolerance will not be tolerated. The problem with just learning how to dimension the parts, how to draw the dimensions, is that as designers, how do we know how to pick the correct dimensions? So most of the class, I want you to wear your manufacturing engineer hat. I want you to think as the manufacturing engineer and figure out how to take those design specifications that the designer gave us and turn it into the physical part. For the next three-quarters of this lecture, 2/3 of this lecture, I want to put on the designer hat and think as the designer who's going to be sending the stuff out to manufacture. And what do we call you guys? Kids with CAD, right? And the reason we call you kids with CAD is because CAD is fun. It's cool. You can draw really cool stuff with CAD. One of my favorite things to do when a kid with CAD gives me a drawing and it's got unreasonable, irrelevant, or occasionally physically impossible dimensions or tolerances on it. They're hardly ever physically impossible, but they're often impractical. My favorite thing to do is say, how are you going to measure that? And when they say, I don't know how to measure it, I say, no problem, I can make it. Right? So that's fun, right? That's me wearing my cranky old machinist hat. No problem, I can make it if you don't know how to measure it. But what we really want to do is we really want to give the customer what they need when they need it. And we can't do that without clear communication. So we want to use GD&T. If you're going to be the person creating the drawings that go out to the vendor, make sure you follow the standards. If you don't follow the standards, it can be expensive. It can be, it's hardly ever millions of dollars expensive with a single incident. Hardly ever. One of my good friends, he said, I don't think you're really an engineer until you've made $1 million mistake. And I think I could go with that. You're not truly an engineer until you've made $1 million mistake. Now, it's easy to make $1 million mistake and catch it before it actually costs $1 million, though, right? But it's easy to make those kind of mistakes. So how do we know what the correct dimensions and tolerances are? Yeah.
Is it just the largest tolerances you can get away with while still having the part be exposed to?
So you said we'd like it to be the biggest tolerance we can get away with and have the part still function. So, and the reason we want large tolerances is because it makes it cheaper to make stuff, right? So if the tolerance is big, a cheaper process can make the part. But how do you know how big you can do it? So designing around what the machine's capable of sometimes comes into play, but I wouldn't do that as a rule if you're the designer. And this is, I've often had this discussion too with people that teach CNC machining or teach machining in general. And the traditional way to do this was to make people spend 2 years learning how to run a manual milling machine before even letting them look at the CNC machine. And I always argued that that was a bad method for doing it because most of the people that are going to get hired are going to use the CNC machines anyway. They're never going to use the manual machine. And two, it sort of drives away the people that like to play video games, the young people we want to hire to go work in our places. But so yeah. How do we know that the thing we've designed has the correct tolerance or has the correct dimension?
So we have 2 parts, for example, in SolidWorks.
Yep.
We can find interactions in assembly.
So one thing you can do is you can actually make the part, and especially if it's an assembly, if 2 things have to fit together, you can make the part and see if they fit together. You suggested we do it in the solid modeling software, which is way cheaper when they don't fit together, right? So you can actually model the part and you can see virtually if they fit together and if the things line up. And so I mean, that's an experiment, right? So we could do an experiment. And there's different ways to do the experiment. We could physically make the part. I mean, it's in the title of the class, right? We talk about CNC machining and prototype manufacturing. So we can experiment, we can make prototypes. Right, so we can experiment, we can make prototypes, and we can see if it works. So that's a way that we can figure out, do we have does it really help us with tolerances? We can see if that instance works, right? We'd have to make a whole bunch of parts to find out the edge of which one doesn't work in both directions. So let's say it's say we've got 2 parts, 2 simple parts, they're square-ish. They've got 4 holes in this part. And maybe we'll do 4 threaded holes in this part. So what thread do you want to use?
Quarter 20.
Quarter 20? So doesn't really conform to the GD&T standard, but it conveys the message, right? So quarter 20 typical, 4. I have to say how many. And now it's pretty obvious when you look at that sketch, not drawing, that's 4 quarter 20 holes. All right. What else do we have to specify in order for somebody to make this? Let's make this part first. Yes?
The location of the holes.
Yeah, so we're going to have to put a dimension here. Oh, let's call that 2 inches. And let's call that 2 inches. Right, so we specified how big the thing was. We'll do a different view that says how thick it is. It doesn't matter for this example. And then we've got to put center lines. This is why I'm an engineer, not an artist. Right, and so then we can dimension, we'll call this 0.5, 0.5, 0.5, 0.5, 0.5. You get the idea, right? So if we're in a ½ an inch, yeah, it's not conforming to the standard.
I was wondering, so we have tolerances for machines, if there's specialty machining.
We don't have, machines don't have tolerances. Machines have capability.
And their tolerances are required because there's like tool wear.
Tolerances are required, well, because it's impossible to know. Tolerances are really required because of measurement uncertainty. So if we could know with certainty what a dimension was, we wouldn't have to have tolerances. We could always make that dimension. But if we can only accept the parts that are that dimension, all the ones that are a little bit bigger and a little bit smaller we can't accept, then we're not going to make very many good parts. And that's because of the capability of the machine tools. So if you have a more capable machine tool or a more capable machining process, you'll be able to make parts with tighter tolerances. If you'll be able to physically make them, but there's really we have to have tolerances. It would be impossible not to have tolerances because we have measurement uncertainty. Yeah, absolutely. The different processes will generate different tolerances. And we'll get to that in about 15 minutes if I stay on track. But yeah, different manufacturing processes will typically have different capabilities. Those capabilities will allow you to hit certain tolerances. And so how does the designer know what the correct dimensions are, right? So this is our idea of a design, right? But we know that it's impossible to make it exactly 0.5 inches from the corners, right? We know that it's impossible. So we're going to have to put a tolerance on it. What do we typically do in ES 1310? Do we typically go to the tolerance block down here? It will say dimensions are in English, 3 place decimals have plus or minus 5, I guess that's 5 thousandths of an inch. We typically just put a little note there. Is that what they taught you to do? And maybe if you have 2 place decimals, it's 50 thousandths of an inch. And if you have 1 place decimal, it's 500 thousandths of an inch. How much is 500 thousandths? Half an inch. Right, so you can have different tolerances. You can call them out right there. If we're the designer, not too far. If we're the designer, so we can pick the distances from the edge based on how strong does it need to be, how much clamping force do we need. We can do some math to figure that stuff out. How much deflection can we withstand? But for the tolerance here, what should we put? You're the designers. Tell me what's the tolerance. On this part, it doesn't matter, right? We could pick anything. When we design the mating part, it will matter. So when you made your cylinders for the Stirling engine, we used a plus or minus 5 10,000ths go no go gauge. So gave you a range of 1,000th of an inch for that diameter. But when you made your pistons, or if you haven't done that, when you start making your pistons this week, you have to measure the cylinder, and then you have to adjust the program to make a piston that matches the cylinder, right? So we made the cylinders and we gave it a big tolerance, plus or minus 1,000th of an inch. Considering our allowance that we have in there is about 8 10,000ths of an inch, we had a tolerance that was bigger than our allowance for the difference in the parts. So you can pick a tolerance here. So let's say plus or minus 1. And so when I say plus or minus 1, what do I mean?
1,000.
I mean plus or minus 1,000th of an inch. So let me draw it as 1,000th. So plus or minus 1,000th of an inch. If we were metric units, what would I mean? If I said plus or minus 1? If I'd mean, yeah. Millimeter? I don't know what I would mean. I hardly ever say that in metric units. I think I would mean a micrometer. But, all right, so if those are plus or minus 1, now, how about these holes? We're going to put this together. We're going to put a bolt through and clamp the two plates together. So what if these were also plus or minus 1? Could we do that? Why not? He says we can't. Who's ever tried to bolt two things together with more than one fastener? Really? Be proud. Who's ever tried to put two things together with more than one fastener? Who's ever had 3 of the 4 fasteners go in no problem and not been able to get the 4th one in? All the same hands are still up, right? What do you do when that happens? Get a bigger hammer, right? Sometimes we get a bigger hammer. What do you do when you really didn't want to hammer the bolt into place? You take it back apart and you take your drill and you waller out the hole, right? You put the drill bit in there and you pull the trigger and you go, right? And everybody that had their hand up has tried that, right? We've all done it. We've all done it more than once, right? But the bolt would fit through the hole, right? So it wasn't that the hole was the wrong size. It was that the hole was in the wrong location. You can fix it by making the hole bigger, right? So there's 2 ways to do this. I could have plus or minus 1 for a tolerance on here, but I'd have to make the hole big enough so that even if this one's out 1 in this direction and this one's out 1 in that direction, so if they're both out 1, the misalignment of the holes is 2, correct? 0.02 of an inch. So how much bigger does this diameter need to be compared to that? So if that's a 1/4 inch fastener that's going through there, the outside diameter of the 1/4 inch fastener is a 1/4 inch. So how much bigger does this need to be? I don't know. I would totally do the math. So if it's 2 thousandths bigger in diameter, or is it 4? Could be out 1. Yeah, 2, 1 in each direction. Absolutely, it's 2. Right. So this one, so the diameter then has to be. Could it be a 1/4 of an inch? The minimum has to be 0.252, right? If the locational tolerance is plus or minus 1 for each set of holes, the minimum here has to be 0.252, right? But we can't make it exactly 0.252, can we? Can we do plus or minus? No, because if it's smaller than that, then it's too small, potentially. Plus, I don't know, how big could it be? So it could be as big as we wanted, right? And it would fit in. But the purpose is to apply a pressure down with the head of the nut. What happens when you've wallered out the hole too much? Right, so then you get a washer, right? And sometimes you have to stack up bigger and bigger washers when you waller out the hole too much, right? So the purpose of fastening them together is for the head of the nut to apply pressure on the plate so that you get friction between the two plates. So especially if these are loaded in shear, if they're loaded like this, it's not the bolts that keep it from falling. It's the friction between the two plates that keeps it from falling. So if you go too big, so how do you know how big is too big? Bigger than the head of the bolt is too big for sure, right? Bigger than the washer that you can fit on the bolt is too big for sure. But also, if you crank down hard enough, what happens? even if it's not bigger. If you crank down hard enough, you end up broaching the part, right? So you can actually, if you've ever put together something with wood and tightened the bolt too hard, you've done this, right? So you could figure out how big is too big. Now, as a rule of thumb, we'll just go a couple thou over, right? We think about how, how accurate is our process, right? So I might say plus 0.001 minus 0. Right, as a rule of thumb, we'll do it that way. And if you do that on all the holes, then you can put this together and it works every time as long as you accurately place the parts. So that's one way to do it, is you can figure it out using math. Now, another thing we like to do in, especially in assemblies, especially in mechanical assemblies, so because we've got, this is not chalk, because we've got this here, let me switch back. So because we've got bolts in all four of these locations, and we've got that big tolerance so we can make sure it fits together, while you're assembling it, the two plates could move relative to each other, right? A little bit. Unless you happen to be bolt bound in all the four directions equally, which is highly unlikely. But they could move around a little bit. What if you need the two plates to locate against each other critically? So what if the location is critical between the two plates? We can't use a bolt. We have to use, we'll use a pin or two pins. One pin will get you location, and the second pin will get you orientation, so you can locate it. And so sometimes you want to put that pin in and you want to drive it in so it'll never come out again. So if we do that, the hole that the pin goes into needs to be bigger or smaller than the pin? Smaller. How much smaller? Depends how much force you want to use when you put it together, right? So it depends how much force. Now, what if you want to be able to put the pin out and put the pin in and take it out again? Because maybe you just want to use the pin to align it while you assemble it, and then once it's in place and the friction is there, you can take that pin out. You don't need it to be in there. Then the hole needs to be bigger than the pin, right? And so actually I get this example. I'll leave it out in the lab so you guys can mess with it next time you come to lab rather than pass it around. I don't think we have time for it to get all the way around. And also in the base for your thermoacoustic engine. So you guys have most of you have finished the base. A couple people still left to do it. There's 3 holes in the top, right? So a 1/2-inch pin in those 3 holes will give you either an RC9 fit. Can you hear this? You can sort of see it. It rattles around a little bit. An RC5, which is in the middle, it rattles around but not as much. Or an RC1. RC stands for running and sliding. RC, I don't know why it's not RS. It's RC. But these are running and sliding fits. These are locational fits that allow you to locate the part but have the pin move in and out. Now, you could figure out what the right dimensions tolerances are by doing some math over here and doing some experiments over here. But I'm an engineer. I don't want to spend all the, I mean, it is kind of cool to make stuff and see if it works, especially when it doesn't work and you get to get the bigger hammer. We actually had I made some pass arounds one summer to share with my M1800 class. We did this talk and everybody was going to have one in front of them. And when I tried out these pass arounds for the first time, it was a plate with 4 holes like this. They were holes that were for pins, and they had different locational tolerances for the different sets of holes. They were all the right diameter, but had different locational tolerances. And I said to the group of students that had them, try to put these together, thinking, try to line them up and drop the pin through. But of course, they tried to put them together. And so now I have a bunch of metal plates that are pinned together with pins, and that was not as useful. So sorry, you guys don't have those. But all right, so instead of figuring it out every time, we can again go back to our friend the Machinery's Handbook. And what are the chances this link's going to work? There's some chance that link's going to work, but it pops up in a different thing and it's not shared. But the link still works. It'll actually, if you're logged into WPI, it'll bring you to the book and you can download it. So perfect. The link works. You can go to the Machinery's Handbook. And look at the section on fits. So we talked about running sliding fits, these RC fits. Here's a graphical indication of how they work. And so there's a table too, you can look it up. But it says based on the nominal diameter, how much bigger does the hole need to be than the shaft for a running sliding fit? If you go back a few pages in the book, there's force fits. Then it's based on how hard you want to hit it with a hammer, how much smaller can the hole be than the shaft? And it talks about how to select the one for the application that you have. So who's gonna make something for their MQP? Probably. Most of you are gonna probably make something for your MQP. Of those people that are gonna make something for your MQP, is it gonna have more than one component? Are they probably going to have to line up relative to each other somehow? There's also sections in here that'll tell you how much bigger the hole should be than the fastener. So you don't have to figure that out. You don't have to do all the math of if I crank down too much, is it going to pull the head of the bolt through the workpiece? So you can look up what's the appropriate, and so we call this a clearance hole. So what's the appropriate clearance hole for this size fastener? And then you can figure out what's the appropriate locational tolerances based on how big you've decided to make your clearance hole. So that, again, is all in the Machinery's Handbook. We talked about measurement tools, and we've talked about accuracy versus precision. I would just note that accuracy here is defined by the ISO as trueness and precision. So trueness is how close to the true value are you. Precision is how close are your measurements to each other. So if I told you to design something and put an RC9 fit for a 1-inch diameter shaft, what are you going to do? So RC is one of the classes. So what are you going to do if for example, what are we doing next Wednesday in class? No, that's Tuesday. What's on the agenda for next Wednesday in class? Yes.
Something about safety?
No. That's tomorrow, Wednesday. Something about safety. Anybody know? It says exam help. Anybody remember way back on the first day that we didn't look at the syllabus, but I told you to go look at the syllabus yourself? There's a section in the syllabus called grading. And in the grading, it says, I think it's the last item on the syllabus. I put little importance on it, but there has to be some importance. We have a comprehensive final exam on the topics that we talked about in lecture. So if the only exam question, for example, was, what's the correct dimension for the hole that you have to make an RC9 fit for a 1-inch diameter shaft, how would you solve that? You'd wait till Wednesday and ask me? Yes. I'd go to the machiner's handbook and look it up. If you're doing the same thing for your MQP, you may not know that you want the RC9. You may just know you need a running sliding fit. You need a locational fit. And so we have this in the lab, so you can come over and say, oh, I want it to be kind of like this. And then you can look it up. That's an RC7, and then you can go look up the dimensions for that machinery in the machinery's handbook. So exam. We didn't do as many quizzes this term as I had, participation exercises as I had wanted to do. We did a few. The exam will be the same format as the few participation exercises we did. The difference is that there I was encouraging you to talk to each other while you were working on it. And on the exam, you should do it on your own. It's worth 10% of the grade, which means it's impossible to get an A without getting at least 1 point on the exam. Right? You have to get at least one thing correct on the exam to get an A, as long as you got everything else correct in the class. Right? And so since most of the grading in the class is about participation, if you did all the lab exercises, if you did the participation quizzes, which are still available if you haven't done them yet, just go do them. And you have unlimited attempts on those participation quizzes, so keep going until you have 100%. Right, so if you did all that, and we start lab exams this week also. To do the lab exam is not intended to have pressure on the lab exam. In fact, there's 5, 6 things that we check off to see, did you do those 6 things? It's the 6 steps on the checklist that we try to remind you to do the checklist every time you're at the machine. If you do all 6 steps on the checklist or skip the ones we tell you to skip because we already did it for you, and you don't crash the machine tool. So if it's about to crash and you hit the stop, you didn't crash the machine tool, right? If you notice during check distance to go that it's not set up correctly and you stop, you didn't crash the machine tool, right? So if you do all those steps, you get 100%. If you forget how to do one of the steps and you ask the PLA, how do I do this? And they tell you how to do that, they take off 5 points. So you could still get a 70, even asking how to do all the steps. So you can still pass the exam, even knowing that you don't know how to, by knowing that you don't know how to do any of the steps. Because the intent is we're always learning when we're working in the labs. And I want you to stop when you get to the edge of your knowledge and go ask for help. And so the exam is not intended to be hard. It's going to be a simple part. It's fixtured in Mill 2 right now if you want to take a look at it, look at the steps. But it's pretty simple. So there's a lab exam, lab exercises, the participation quizzes, and the final, and the group project, right? Group project next Tuesday. Everybody's going to present? Okay. Each group. At least one representative from each group will present. It's awkward when you have 8 people standing up here and you pass the microphone back and forth between each other, but you can decide for yourself if you have a great spokesperson for the group. Some general feedback on group presentations and stuff like that. So we got just a minute left, just exactly a minute left. Look like you took it seriously when you're doing the presentation. So like shorts and flip-flops, if you already own a $10 million software company and you're talking to your customers that pay $97 a month for your software, then maybe you can come in and wear shorts and flip-flops to the presentation. But since you're proposing to the bank to get the money to start your business, I don't know, wear a shirt, wear pants. comb your hair. I mean, sorry, you don't have to comb your hair. You could shave it off like me. All right. I'll see everybody here tomorrow. We're going to talk about safety systems.